Welcome to this explainer. Today, we're diving into what is arguably the most formula-dense unit in the entire JEE main syllabus, properties of solids and liquids. If you've ever stared at a giant wall of physics equations and just felt totally overwhelmed, you are definitely in the right place. So how do you actually master the most formula-heavy unit in physics? Well, the secret is simple. You have to stop trying to memorize a dry, disconnected cheat sheet. Instead, we're going to turn those equations into a logical, high-energy journey of physical transformations. We're going to see exactly how matter behaves when it's pushed, pulled, pressurized, and heated, which will give you the deep conceptual edge you need for the exam. Here's our roadmap for today. We'll start with the rigid rules of solids, bending without breaking. Then we'll flow into fluids, pressure, and flow. After that, we'll look at surface tension with drops and bubbles. Then we'll turn up the heat with thermal physics and heat transfer. And finally, we'll wrap up with strategies for acing the JEE main. Let's get right into it.
Section 1. Solids, bending without breaking.
Okay, let's start with the foundational concept of elasticity. Materials handle stress completely differently. Just look at ductile materials like copper. They're incredibly resilient. They yield gracefully and stretch out into long wires. But on the flip side, you have brittle materials like glass, which don't really stretch at all. They just snap and crack right under the pressure. Quick pro tip, be resilient like copper. Don't be the glass during your exam. Now let's talk Hooke's law. This states that stress is directly proportional to strain, and we actually measure this using 3 specific constants. You've got Young's modulus, which measures stiffness, so the higher the Y, the more rigid the material. Then there's the bulk modulus, measuring resistance to a change in volume. And finally, the shear modulus, which is all about rigidity against twisting or parallel forces. These 3 are absolutely foundational for solid mechanics. But you have to watch out for this trap on the stress-strain curve. There is a massive difference between the yield point and the breaking point. If you push a material past its elastic limit and hit that yield point, you enter the plastic region. That means permanent deformation. It's never going back to its original shape, even before it actually snaps at the breaking point. Keep those definitions sharp. All right, moving on to Section 2, fluids, pressure, and flow. Now, fluid pressure brings a whole new set of rules, and here is a major JEE trap to avoid. Look at the formula. P equals H times rho times G. Notice what's missing. The shape of the container. Pressure depends strictly on the depth and the fluid's density. Whether you're in a massive swimming pool or a tiny glass tube, if the depth and the fluid are the same, the pressure at the bottom is exactly identical. Don't let those tricky diagrams fool you. And when it comes to fluid flow, keep this magic number in mind. 2,000. That's your Reynolds number boundary. If you're below 2,000, you get a beautiful, smooth, streamlined flow. But push that velocity up and cross 3,000, complete chaos. It becomes a turbulent flow full of random eddies. It's a simple threshold, but absolutely crucial for fluid dynamics. Now, Bernoulli's principle. It's not just some random equation. It is the ultimate fluid energy conservation law. This one principle explains how airplane wings actually generate lift, why your atomizer sprays perfume, how a carburetor works, and even the swing on a cricket ball or a chimney draft. The core idea? When fluid speed goes up, pressure goes down. Master that, and these applications will make perfect sense. Up next, Section 3, surface tension, drops, and bubbles. Zooming in on the boundary of liquids, we find this weird behavior governed by cohesive forces. This is surface tension. Essentially, the force per unit length, or the work done to increase surface area. Basically, the surface acts like a stretched elastic skin. That's exactly why water drops form little spheres. They're just trying to minimize their surface area. Exam alert right here. You'll definitely see excess pressure questions. The excess pressure inside a liquid drop is 2T over R. But look at a soap bubble. It's 4T over R. Why the doubling? Because a liquid drop only has one outer surface. But a soap bubble is hollow. It has an inner surface and an outer surface. 2 surfaces mean double the surface tension force. Seriously, don't let them catch you slipping on this one. And this perfectly explains capillary action. Put a glass tube in water, and it rises up the tube because the angle of contact is small or acute. But mercury? Totally different story. Put a tube in mercury, and the level actually falls due to its obtuse angle of contact. The mercury wants to stick to itself way more than it wants to stick to the glass. Let's keep moving. Section 4, thermal physics and heat transfer. Before you do any single calculation here, burn this number into your brain. 273.15.
To safely use thermal equations, you absolutely have got to remember to add 273.15 to convert your Celsius temperatures into Kelvin. Forgetting that step is literally the easiest way to throw away marks.
What's really cool is how perfectly thermal expansion scales mathematically. Heat causes things to expand, right? Well, for 1D linear expansion, the formula uses the coefficient alpha. For 2D area expansion, it just becomes 2 alpha. And for 3D volume expansion, it scales right up to 3 alpha. Once you know the pattern, you instinctively know all 3 formulas. Now, when heat actually moves, it does so in 3 main ways. You've got conduction mainly in solids, where heat transfers without the matter itself moving. Then convection, which is the actual movement of fluids, think sea breezes, and finally radiation, which needs no medium at all. That's exactly how the sun's heat travels through the literal vacuum of space to reach us. Finally, Section 5, Acing the JEE Main. Having a solid strategy is half the battle. Here are the top formulas you absolutely must memorize. You've got Young's modulus, Bernoulli's equation, the capillary rise formula, and the classic Q equals mc delta T for heat. These are your heavy hitters for this unit. You need to know them backward and forward.
So what's your actual game plan? Step 1, memorize those key formulas. Step 2, practice numericals heavily. Step 3, really understand your graphs, especially the physical meaning behind stress-strain curves. And Step 4, rigidly check your SI units. One mismatched unit will completely ruin a perfect calculation, so always double check.
Because ultimately, when you take a step back, this stuff is everywhere. From the bridges we drive on yielding to pressure, to the heat radiating from your morning tea, these aren't just dry exam questions. They are the fundamental rules that govern our physical reality. The real question is, how will you use these equations to master that world? Thanks so much for joining me on this explainer. Keep up the hard work, and I'll catch you in the next one.